Hello and welcome back. Here we are. Week 9 was break. Week 10 here in statistics for psychology. We are now getting into some of the meat here. Chapter 9, the normal distribution and z-scores. Like I know some of you have already been interested in these z-scores and whatnot. I'm going to try and explain this as more straightforward as I can. It actually really is not that complicated of an issue. See if I can pull this off. I'm going to use the example here of standardized scores, standardized testing, for example, like IQ. There's all kinds of IQ tests that go out there that have all kinds of different numbers of questions, all kinds of different scores that go on, but those scores are transformed into a standard scale that we know of as IQ. And that IQ has a mean of 100 and a standard deviation, I think it's 15. So an IQ, like I could have got a 72 on an IQ test, but then that's transformed into Z scores, basically. That's how the table for IQ is created. And so you have 100 is in the middle, 115 is one standard deviation above that, another 15 is 130, two standard deviations above that. Maybe it's 10, 110, 20, 30 standard deviations. And it's in that IQ score that 100 to 110 is one standard deviation, and those score that 70 something, that 78 that I got, is placed somewhere on that scale. So when we take raw scores and we convert them to standard scores or Z scores, what we are doing is we're changing the unit. I'll use another example. Let's say we're looking at something that has its weight in pounds, and then you have something that has its actually mass in terms of kilograms. Okay? There's a formula that converts pounds to kilograms, and you can go back and forth with those. Now, we're using a unit of pounds, and we're considering it a unit of kilograms. Whatever unit you're talking about in the original data, we are converting it to units of standard deviation. How many standard deviations? So you look these numbers from the mean, which is 0. You have a score of 1, which is one standard deviation above, and you have minus 1, one below. 2 above, 2 below, 3 above, 3 below. And then when we take our raw score and we convert it and we plop it onto that graph, we know that if the score is way closer, 2, 3 standard deviations above or 2, 3 standard deviations below, that means those scores are pretty rare. We've already determined that when we looked at the normal curve. And what that allows us to do is to take any unit, put it on this scale, and determine whether our score is rare. That's the basic standard that goes on. So let's look. There's a formula, and I've included it in the course book here. The z-score is equal to the score you're looking at, that's the x, minus the mean of the mean of the population, the standardized test, divided by the standard deviation of that. Okay? So there's our formula. We have an x, and we know the mean and standard deviation of the distribution from the standardization process of the test. That means I can take my score, whatever it is, I can put it into that formula with all those things and solve for z, which is going to be that score in units of standard deviation. Okay? Now when we look at, I gave you an example here, we have the standard scores for dogs' weight. We have human males and females in terms of standard scores. And we have here I can now compare based on my placement in my own standard method. So as a human male, where am I on that in terms of how far am I from being normal? And I can compare to my dog, which how far they are away from normal. So I can compare one species to the next based on our own placement within our own distribution, the variability of weight between those two areas. We can look at two different scores in an IQ test and do the same thing. How do they both relate to standard scores based on that test? This is the way this using standard scores is a really useful way to take our single score, either from an individual or from a sample, and compare it to the normal distribution of those scores when we use a standardized test. Okay, now this all assumes that we have that standard data. I'm able to do this particular task, comparing my weight to a dog's weight in terms of standard deviation, because we have in possession the data of the standard deviation and mean of dogs in terms of weight. And we have the same thing, standard deviation and mean in terms of humans. That's how we can do this comparison. So I can figure out how many standard deviations above or below the norm I am and compare it to how many standard deviations above or below the mean my dog is and see where we are with that. Okay. So in order to do this transformation, we have to know the population mean and standard deviation. So that's going to be, now I get into here, show you some, I'll just go through the course book here because it's that detailed here. So you have raw scores to Z scores in Excel. So here's a group, okay? I'm a doctor and I'm starting a weight loss program. According to my data, we already have the population of women has a mean of 140 pounds with a standard deviation of 25. Then those are my mean, those are my population mean and standard deviation. This is my raw data. Okay? So I open up a workbook, I put all the weights there, and I just wrote down population mean, population standard deviation, and I just plug it in. There's a function called standardize, okay, where I put I put A2 right here, that whole column, and then 140 is the population mean, 25 is the standard deviation, and it'll average all that together, and it determines that the mean of these is 0.8 standard deviations below the mean. Okay, so that's showing that this particular group is significantly below the mean. There's also in there a link to a thing called the standard norm table. And even when I was first learning statistics, I found this sort of bizarre because if you look at the standard norm table, it gives you all the ways in which your results can come out when you're doing this kind of transformation. You're getting a z-score. What all the numbers in the table, let's take a look at that. Take a look at the actual table. What all these numbers represent is the percentage of data that is to the left of that particular point on a standard table. So let's see if I can zoom in on this here. Okay, so right here, the 0.3 z-score over here means that from that z-score under the 0.05 significance level, it's 0.3 here, 63.68% of the data is to the left of that point. Now, this is just giving you the positive side of the curve. You can just put negative numbers on the other. It's the same thing. So whatever the z-score is, you might get a z-score of minus 2.5, If that's the case, then you just convert it to 2.5, go down here, and we go to 2.5 positive, and these are the numbers that apply to you. It plus or minus doesn't really matter. In the end, though, all you need are two numbers. And I've supplied them for you in the course book. Let me get back to the course book here. Put them right there. If you are going to use the 0.05 criteria for significance, your converted z-score has to be 1.6 or higher for it to be significant. If you are going to use the 0.01 level, it has to be 2.4. So what this means is I have a sample. I take you as a group of students and I give you an intelligence test. And I convert that mean, the average, the mean of your intelligence test to a standard score. And I want to see if you as a group are significantly more intelligent than the average group. So I convert that to a standard score, and I get a score of 1.75. Now, I made the decision as a researcher that I'm going to hold myself to a very high standard. I'm not going to consider your score to be significantly different than the average score unless it meets the 0.01 level of criteria, meaning it's got to be that much more different before I'm going to call it significant. That's a choice I have as a researcher. So your mean score comes out to 1.75. And if I was at the 0.05 level of decision making, that would be a higher number than the 1.6 criteria to meet that. So if I was going by the 0.05, yes, the group is significantly different from the mean, but I'm not. I'm using the 0.01 criteria, a much more stringent criteria before I'm going to call things abnormal, even if it's a positive thing. And the 1.75 is below the 2.4 level that's needed for significance there. So the results remain the same, but I hope you see in that example, depending on which level of criteria you've chosen, one is a significant result for the lower criteria, and it's not a significant result for the higher criteria. All you need to know is 1.6 and 2.4. Those are the ones. Of all those numbers, 1.6, 2.4. Those are the z-scores you're looking for when you're using a z-score test to compare to a standard test. Those are the z-scores that you look for to determine significance at the 0.05 or 0.01 level. Now, keeping in mind that significance means that this particular score, whether it's a mean score of a group or a sample, whether it's an individual score, is far enough away from the mean, in one case 1.6 standard deviations from the mean, to meet the 0.05 criteria, that this is rare to the point that it is higher than 95% of what we would expect, that 5%. At the 1.01 level, it's so far from it's so far from the mean, it's 2.4 standard deviations above the mean. That means it's different from 99% of everybody else that's taken that test. That's how we define the 1%. That's where that comes from. Woo! That 1% is that are so different that 99% of people are below that. So you look at the 1% financially, it means that 99% of the population has less money than they do. That's where we act. That 0.01 is actually where we get that phrase, the 1%. So when we use z-test, just like I said, let's say I wanted to make a determination as to whether this class had an unusually high intelligence, I would set my criteria. Am I going to pick 0.05 or 0.01? I would transfer those tests into z-scores and see how many standard deviations you are above. And if it's the 1.75, you do not meet the criteria for the 0.01 level of significance, but you do meet the criteria for the 0.05 level of significance. And that's how we make decisions about whether people are significantly different, or that, I do an intervention to help people understand statistics better. I compare it to the whole history of how people have done on that test before. That standard deviation, that mean, compare the mean of the new group to see if my new method is actually significantly improves scores or not. And I set that criteria based on the 0.01 or 0.05, and that will tell me how much better. It's an interesting thing to know that, let's say, when you're getting ready to take the graduate record exam or the SAT, there are classes that you can sign up for that teach you how to take that test. Get practice exams, you're doing all that stuff. What's interesting is it's actually pretty rare that the change in score between what you would have scored before that training and the score after that training is so large that it's a significant change in your grade. So there's some research to support that those are not worth it. That the change in the average change over time that occurs that would be filled up with this training program or filled up with just normal life is not significant to justify the cost. That doesn't mean they don't work for some people, because for some people they're transformative to get over test anxiety and whatnot. But those kinds of preparations are really meant for individuals who have trouble taking tests. They don't necessarily prove themselves to be very effective at actually increasing people's score. The skills that it takes to have that developed over a very long time of your education. So, Chapter 9 discussion, I want you to go into EBSCO and I want you to use z-scores as one of the search criteria and find an article that uses z-scores. What they're going to be doing, if they're doing a z-score test, that means they are using as one of their measures a standardized test, either one they've developed themselves or they're using an existing standardized test from which you can get the mean and standard deviation of how people perform on that test. And I want you to research that and discuss what you find out. In the quiz, let me go to the quiz here. In the quiz, I'm having you use that formula from the formula I want you to use is this one right here. The Z equals X minus mu over sigma. I think that's what those are, mu and sigma. Okay, I want you to use that formula right here to calculate here's the standard height for men over 20. 69 inches is the average with a standard deviation of 3. Here's the standard of weight for men, 190 pounds, standard deviation of 36. Suppose you are 5'7", male who weighs 180 pounds. You want to know if you weigh more than you should. You are going to calculate your z-score for height and your z-score for weight. You are not going to use your own real height and weight. You are for the sake of this assignment, you're a 5'7" tall male with at 180 pounds. I'm not trying to be discriminatory. I just built the assignment that way. So you're 5'7", male, 180 pounds. What's your Z-score on height? What's your Z-score on weight? What's going on? Draw conclusions about your height. What is that standard deviation? Are you over, under? Is it beyond the 1.6? Is it beyond the 2.4 for the 0.05 and 0.01 levels of significance that you could say I'm significantly taller at this level of significance, 0.05 or 0.01? I'm significantly heavier. You see the average weight is 190. They're 180. Are they significantly lighter than the average male at 5'7" at the 0.05 or 0.01? Those are the questions you want to answer in this particular quiz. Okay, and because we are so excited about this class, we're going to take on another chapter. That is chapter 10, where we are going to compare z-tests to t-tests. Now, z-tests is when we know, this is it, it's the whole thing. Z-test is when we know the mean, but we don't know the standard deviation. We might know the average of something, the average amount that something takes place, but we don't know the standard deviation. At that point, and here's the thought process that goes into, so follow me on this. We take the standard deviation of the sample and we use that instead of the population standard deviation. That's all we do. The population, the sample standard deviation is an estimate of the population from our sample. So the size of our sample, knowing that large samples, the standard deviation within large samples will gradually over time approach the population standard deviation in terms of accuracy until our sample is the size of the population. So the size of our sample plays a role in determining that score, because we're going to use the sample standard deviation as a substitute for the population standard deviation. So we enter into this here. Let me get caught up. When we have a standardized test that gives us the mean and standard deviation of something, that's what we go with. We go with z-scores, and that's how we make our decision. When we don't have that, we have to go with a different formula. This is why standardized tests are so popular, because standardized tests are really, really easy to use. So as you were looking at your research projects, if you were able to go in and find a test that exists out in the world and use that as one of the measures for your study, you're able to use z-scores. You're able to just make that conversion using the formula that's built into that test, and there you go. You're all set in terms of whether you have significant results or not. If not, if you just have, it's called a one sample t-test, we're going to compute a t-score, which is an estimate of a z-score based on a formula that uses the standard deviation of the sample as an estimate of the standard deviation of the population. I'm glad I actually got to say that without making a mistake. So let's hear. So on page 213, I introduce both the formula right here. Here's the same, it's the same formula, like the t instead of a z, the x here is the mean of your sample or the score. Just take that little line away and it's not the average, just the score, minus the mean that we know of the population divided by what is called the standard error. This is the sample standard deviation divided by the square root of the sample size. So this formula right here is the t-score, which is just like a z-score, but when we don't know the standard deviation in the population. Now over here we have the example. We have a superintendent that wants to evaluate if the number of COVID cases in their school, how that compared to the national average, and they know that the national average is 6.1. What they don't know is the standard deviation. It's actually much more difficult to get that from the kind of data that they collect when they're looking at that kind of data. So here we are, we have the 6.1% nationwide average. How is my school? I'm the superintendent. How is my school doing in terms of the number of cases? So I introduced the data. School 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here, I'll have, and there's my data right there. That is the percentage of students in each one of those schools that has COVID. Okay, so first I do my descriptive analysis here. I select all this information and I use the data analysis tool pack to compute my descriptive data. So my mean is 6.53 and the standard deviation is 0.99. Okay, so let's look. So 6.53, let's look back a little bit. The average is 6.1. Mine was 6.53. The national average is 6.10. So the incidence of COVID in my school district is higher than the national average, but I don't know if it's significantly higher because I don't know the standard deviation there. So I'm going to calculate a t-score that allows me to determine whether or not my score, my average, is different from the national average. So I go through that. Here's the formula. And it comes down to a t-score of 1.42. This is very similar to z-scores. Now the z-score line in the sand, remember from the z-scores, was 1.6 or 2.4. I hope I remember those correctly. 1.6, 2.4, that was the 0.05, 0.01 level of significance. What we want to do now that we have this, we want to use what the t-table. Now, what this is going to introduce is going to be something that's a little quirky, and that is the degrees of freedom. What the degrees of freedom refer to is when we're looking at a study, and in this study, we're looking at, we took 10 samples, okay? The average of those samples, no matter what those numbers are, like, follow me on this, no matter what those numbers are, all the nine, the first nine can be anything in the world, but to maintain the average that we've calculated, one of them those nine would define the last one. So they could be all over the place, and that last number defines what the average is of that. Just a mathematical reality, okay? So when we have one factor that we're looking at, we take the n minus 1, and it says that all of those 9 values are free to vary, but then that variability determines the one that has to, in order to maintain what we've identified as the average. It's just a mathematical observation. But we use that figure, the n minus 1, as the degrees of freedom, and it allows for taking into consideration, when we're looking at variability, the fact that this is a sample. The bigger that number is, the less that 1 is going to affect. So if it was 5 minus 1, it'd be 4. That'd be our degrees of freedom. But if it was 10,000 minus 1, it would be 9,999. So we're taking into account the size of that sample as we're trying to estimate what the population would be like. So that's the purpose of degrees of freedom. In a study, we'll have a degree of freedom. Wait, the minus part is how many variables are in that study. So here we're just looking at one variable. If I'm looking at 5, it'd be n minus 5. So for each one of those variables, there's one number that gets defined by the rest of them. And that's how we calculate degrees of freedom. So if we go to, if you don't understand that yet, that is perfectly okay. You just need to know that you have to, when we use this table, when we use the T table, we're going to have to take in mind the degrees of freedom. Okay, so here's the table. So in our, what did we end up with here? Get the book out again. I keep closing the course book. I don't know why. We ended up with 1.42. That was our result. So let's go to here. 1.42, n minus 1 is 9, so we have 9 degrees of freedom, and our t-score was 1.42. So we go to 9, right there. I'll move in. Here's 9 degrees of freedom, and we go over to 1.42. Whatever's close here. We have right there, we have 1.38, and then the next one up there is 1.83. So 1.42 is in between those right there. Okay? Now, right here, if we're doing a one-tailed test or a two-tailed test, right here, the level of significance is 0.1, and this is 0.5. This is the magic one right here. 0.5 there, 0.1 there, and a one-tailed test, and then 0.5, 0.01 level there. So my t-score would have had to be above 1.833 in order to meet the 0.5 criteria of significance, or it would have had to be above the 2.8 level to meet the 0.01 in a one-tailed test. In a two-tailed test, my score would have had to be above 1.833 to meet the point, right there. It'd have to be above 2.262 to meet the 0.05, and it would have to be above 3.250 in order to meet the 0.01. Now, I said at the beginning, the researcher, the superintendent, wanted to know if his scores were different. He was okay with them being significantly below or significantly higher, whichever. What we have found out is in both of these tests, the score, the t-score that he got, or she got, was not significant. So even though the average was higher than the national average, it wasn't high enough for it to be significantly different. So yes, the number of people who got COVID was higher than the national average, but not statistically significantly so. It was still within that range of normal variance. So there we go. That's what we have. I hope that helps. I hope I did a good job with that. So, in the assignment, let me get to the assignment. I'm having you look at in the assignment, I'm having you look at data representing a study done on ESP. Now, the clue here is I don't give you the population mean, but you can figure it out with logic, because you can figure out on pure chance what is the likelihood that someone will have seen or not seen the advertisement? As guessed or not guessed what was happening in the ESP situation. So they were either right or wrong. So if people were guessing, what will be the average number of right answers? There's some logic to that. Okay. And then you put it into that formula and you determine whether or not you have significant results or not. And that is my computer just freaked out. So I can't show this to you. I'm going by memory here. So if I'm a little off, there's been a number of assignments I've done this. One of them has been, I did an assignment like this that was once about the subliminal perception. So I might be getting that one mixed up. I think this one's about ESP and being able to guess whether something is there or not. Either way, it's the same thing. When you're looking at guessing, what is the likelihood that you're going to get it right? That's your population mean. Don't know the standard deviation, you can still compute the t-score and you can still determine whether or not your results are significant. Two-tailed or one-tailed, the degrees of freedom, going over and seeing whether the t-score is high enough for it to surpass the level of the 0.01, 0.05 criteria for significance on either a one-tailed or two-tailed test. So, with that said, 2 chapters of stuff. Good luck with that. I'll see you in the discussion boards. Have a great week.